Okay, welcome back everyone. In this video, we're going to go over an example of how to solve a Newton's second law problem with inclined planes. And so this kind of goes back to way back in chapter 3, number 47, where we had a weight vector, which we had to divide up into components. And so you'll see what I mean in a moment. In this problem, we have a car which is moving up a hill, and this is actually number 71 on page 135, and it says a car coasts with the engine off up a 30-degree grade. If the speed of the car is 25 meters per second at the bottom of the grade, what is the distance traveled by the car before it comes to rest? So we have v final is equal to 0. And we want to find the distance it's traveled up the hill, up the grade, which in this case is parallel. So if we identify the forces that are acting at the car at any particular time, there's no friction on this hill, and we have a 30-degree angle. But we do have the force of gravity, and we also have the normal force. Now the force of gravity points directly downwards, and the normal force for an inclined plane will point perpendicular or normal to the surface. So these are the two forces that we have. The problem is that if we want to talk about things going up the incline, kind of in this direction, that's our parallel direction, and perpendicular to the incline is our other axis. So we don't really have a coordinate axis that's like x and y anymore. We don't really have that. Instead, what we have are these perpendicular and parallel directions. And so the problem is that the normal force is just fine. It goes in the positive perpendicular direction. But gravity is an issue because the force of gravity goes straight down, but that's not aligned with our axes. So what we have to do, let me zoom in a little bit more. What we have to do is take gravity and break it down into components. Get a different color here. And so we're going to have what we call FG perpendicular, and we're going to have FG parallel, and those make a right angle. And we can show that the angle at the top of this triangle is also 30 degrees. And so we can use this to calculate the components of FG perpendicular and FG parallel. And again, if you're unsure about what's going on here, go back and look at number 47 of chapter 3. So in any case, what we end up with is that FG parallel is equal to mg times the sine of 30 degrees. mg is the force of gravity, or the hypotenuse, and then we have the sine of 30 degrees because it's opposite the angle. FG perpendicular is equal to mg cosine of 30 degrees. Okay, so now we go back to our original problem, which is to find the distance traveled up the incline. So we have to apply Newton's second law twice, and we're going to say that the net force parallel to the incline will be equal to MA parallel to the incline. Likewise, the net force perpendicular to the incline will be equal to mass times acceleration perpendicular to the incline. And now we have to think carefully about what we have in each direction. So the net force parallel to the incline, it looks like the only force that we have, which is going parallel, is the parallel force of gravity. That looks like the only piece that we have. So we just have minus FG parallel. And the reason that I put a minus sign is because this particular force is going down the ramp. and that's in the negative direction if we say that up the ramp is positive. So that's equal to ma, and then what we can do is say negative mg sine of 30 degrees is equal to ma. And let's hop on over to the perpendicular forces and see what happens there. On that side, what we have are two forces. We have the normal force, which is acting in the positive direction, and we have Fg perpendicular, which is acting into the incline, which is the negative direction. So that's going to give us a net force, and we want to think about which way the car is accelerating. It's actually accelerating parallel to the incline, not perpendicular, so it's not flying off into the air, it's not tunneling into the incline, so its perpendicular acceleration is 0. So in many cases this will happen. The normal force is equal to Fg perpendicular. Okay, so the normal force is equal to mg cosine of 30 degrees. And in general, when you have a situation like this, it's mg cosine of theta. Now you have to be careful, because if you have a situation where you're pushing onto the car with an external force, then this isn't necessarily true. But one thing we can see about this expression is if gravity and the normal force are the only thing acting perpendicular to the incline, we get some weird things going on. For example, if the angle is 0 degrees, what would a 0 degree incline look like? That's right, it would be a flat surface. So in that case, this would tell us that the normal force is equal to mg times the cosine of 0 degrees. And the cosine of 0, check it on your calculator, is 1, so the normal force would be equal to mg. And so this gives us a pretty familiar result, that on a level surface, the normal force is equal to the force of gravity. Another neat thing about this is, let's say we're talking about 90 degrees. So we have a vertical surface. Well, in that case, it's kind of weird. The normal force is mg times the cosine of 90 degrees, which is 0. So in that case, the normal force is equal to 0. And that kind of makes sense, because the normal force is kind of going out this way, but if we have a vertical wall, then our object is going to be falling straight down, and there's no contact really between them. Okay, so back to the problem at hand, we actually want to find the distance the car travels as it comes to rest. So now we have to go back to the parallel equation, and we don't have the mass, which seems like it would be a problem, but it actually cancels out. And so what we get is that the acceleration is negative 9.8 meters per second squared times the sine of 30 degrees. And that happens to be negative 4.9 meters per second squared. So if you remember in the Zany-Zircon-Zinger's lab that you had an acceleration, but it wasn't 9.8, well, the steeper your ramp was, the more acceleration you had, and the shallower your ramp, the less acceleration. And what does it depend on? Well, it looks like the sine of the angle. So if you had 10 degrees, it should have been 9.8 times the sine of 10. So in any case, how do we find the final answer? How do we find the distance that it's traveled? Well, this is a 1D motion problem. Okay, we have an initial speed of 25, we have a final speed of 0, we have an acceleration of 4.9 meters per second squared parallel to the ramp, okay, and we're trying to find the distance it goes. Well, it's been a while since I've done kinematic equations, so I think I forgot. Haha, we're going to use the forgotten equation. So v final squared equals v initial squared plus 2a delta d. So delta d is v final squared minus v initial squared all over 2a, 0 minus 25 meters per second, quantity squared, divided by 2 times negative 4.9 meters per second squared. And we plug and chug, and that gets us just about 64 meters, which is in the positive direction, which is up the incline. And that's exactly what we hope to get.